In the last two videos, we looked at valence bond theory as applied to a one-dimensional molecule, linear beryllium hydride, and a two-dimensional molecule, trigonal-planar borane. In this video, we're going to talk about its application to a three-dimensional molecule, methane. So our process starts off the same way. We need a Lewis diagram for our molecule of interest, and then we need to use VSEPR theory to determine its geometry. So in methane, our carbon atom is attached to 4 different hydrogen atoms, and it is tetrahedral in electron group geometry and also in molecular geometry. And those bonds are all 109 degrees apart. There aren't atomic orbitals on that carbon atom that can be used to justify 109 or 109.5 degree bond angles. In order to do that, we have to take the atomic orbitals and recombine them to make hybrid atomic orbitals that will have that angle between the directions in which they're pointing. So what we're going to do this time is take all 3 2p orbitals and combine them with the 2s orbital. And so if our carbon starts off with those 4 atomic orbitals, or 4 valence atomic orbitals, they are all going to combine to make 4 hybrid atomic orbitals. And since there's an s and 3 p's in each of them, they are all called sp3 hybrid atomic orbitals. How do we get there? Well, let's look at the construction of one of them. I'm going to start by combining the 2p orbitals that are easiest to draw. So the one pointing up and down and the one pointing left and right. And this picture is going to look fairly similar to the one in the last video, in which the upper right lobes combine in phase and the lower left lobes combine in phase. And that essentially winds up tipping our orbital on its side so that it's pointing at an angle. Then if I add the third 2p orbital to that, there's going to be positive overlap, constructive overlap between the positive phases, and destructive overlap between the positive and negative phases. And what that's going to do is it's going to take our orbital and tip it forward. And I'm not going to attempt to draw that. I'm simply going to leave you a note for that, because I have some beautiful computer pictures in a couple of slides that will show you that without you suffering through my attempts to draw it. So if we then take that shape that we've generated from combining the 3 2p orbitals and mix in some 2s, that's going to have the same effect that it's had in the last couple of videos. It's going to make the shaded lobe larger and the unshaded lobe smaller. So this is going to make one lobe larger and one lobe smaller. Now, we've taken 4 atomic orbitals and combined them, and we are showing or talking about 1 hybrid atomic orbital. But of course, you can't take 4 orbitals and make 1. You have to take 4 orbitals to make 4. So our overall picture says that we take a 2p and another 2p and another 2p along with the 2s. Combine an S and a P and a P and a P to get 4 sp3 hybridized orbitals that are going to look, generally speaking, that sort of a shape, but each pointing at different hydrogen atoms within the tetrahedral molecule. So how does that play out in the bonds? So we've now made hybrid atomic orbitals that are all 109.5, give or take, degrees apart. We've got one pointing at each of our 4 hydrogen atoms. I'm just going to draw one of them on this picture here. So we have an sp3 on the carbon, and that is able to combine with a 1s orbital on the hydrogen. And that will make a sigma bond because it's an in-phase or constructive interaction, and it's sigma symmetric. This happens 3 more times, 1 for each bond, 1 using each sp3 hybridized atomic orbital. So my overall picture is going to have another sigma bond on this CH interaction and another sigma bond on this CH interaction and one last sigma bond pointing on this CH bond back here. And so each of our 4 sp3 hybridized atomic orbitals can be imagined to be contributing to 1 CH bond.